Let's talk about RC discharge and charging circuits. A discharge circuit is one where you have an inductor that has got an initial current I and it's fully currented up, and then it discharges some of the current through the resistor R attached to it. A charging circuit is one where you take the inductor that's completely empty initially, let's say, and you try to charge it up by putting, or rather current it up by putting a battery. So there's going to be a current flowing initially, and then eventually it'll all get charged up. Now, before we go any further, I want to look at the energy stored in an inductor. So here's how we do that. The energy stored in the inductor is magnetic energy. So the rate of change of that magnetic energy, or magnetic power if you will, is the voltage across the inductor times the current in the inductor. Now, by Henry's law, the voltage across the inductor without the Lenz's law sign is L di by dt times I, and this by the rules of calculus can be written as 1/2 L d by dt of I squared, because if you do d by dt of I squared, I'm going to get 2I di by dt, and the 2 cancels the 2 and gives you back this expression. So I can integrate both sides. When I integrate them, I get UB equals 1/2 Li squared. Now, expressions like this makes physicists very excited, because if you think about the current as dq by dt, rate of change of charge, then this looks exactly like kinetic energy. Kinetic energy is 1/2 mv squared. The 1/2 is there. So we are forced to conclude that mass inertia for an object that's moving is similar to electrical inertia or inductance. The laziness that an inductor feels letting current through is similar to the laziness that an object feels getting to move in the first place. So velocity is dx by dt, and that completes the analogy because current is the same as velocity and charge is the same as distance. So that's a great way of looking at things. So to pursue this analogy, let's try to do this for the discharge circuit. What I have here is a mass m moving initially with some velocity v, and the resistance can be thought of as an air drag. It's important to think of resistance as something that depends on velocity. Air drag does depend on velocity. Regular friction, mu times the normal force, does not depend on the speed. So this is an appropriate situation. If you try to solve this air drag problem in mechanics, you'll get the exact same expressions that you get here in this case. So that's one of the great advantages of doing everything using analogies. Okay, now let's proceed and solve the discharge circuit. In the notes, I go ahead and use KVL for this, but let me try to do this using energy again. So the rate of change of magnetic energy in the inductor will be equal to the power dissipated in the resistor, and with a negative sign, so that's negative I squared R, because dissipated power is negative. So I can now substitute du by dt, which is right here. Du by dt is the very first line, so it's L di by dt times I equals minus I squared R. Cancel out the i's and bring everything to the left side. I get, and first I'll divide both sides by L and then bring everything to the left side. So I get di by dt plus R over L I equals 0. Now that left hand side has got current over time. Therefore R over L must be 1 over time, which means I can define a quantity called the time constant of the RL circuit. Tau RL, or simply tau, is L over R. This is the time constant of the RL circuit. In terms of the time constant, then, I can write my equation as follows. It's di by dt plus I over tau, I won't write the RL, it's understood, equals 0. Now this equation can be pretty easily solved using what's called separation of variables. So I write this as di, I take first this to the right side, so I get di by dt equals minus I over tau and then I separate the variables. So I'll get di by I equals negative tau dt. We are done almost. Integrate both sides. If you integrate both sides, you're going to get a constant of integration. So I'll get natural log of I equals minus, excuse me, that's 1 over tau, so tau inverse. That's going to be t over tau plus the constant. Now the constant I'm going to write as natural log of something. Natural log of constant. Please don't confuse this with capacitance, it's constant. So, so maybe I should write this as con. It's more writing, but it's worth it. So if I take the exponential of both sides, I'll get I equals exponential of a plus b is exponential of a times exponential of b. So when I take exponential of natural log of con, I just get con. So I'll get con times e to the minus t over tau. We have to fix con using initial conditions, and the initial condition is that at time t equals 0, the current was the full current I naught. So that's the initial condition. At t equals 0, I of 0 equals I naught. Substituting that, I'm going to get I naught equals con e to the minus 0, which means con is the same as I naught. So I have the full equation now. I as a function of t equals I naught e to the minus t over tau. Beautiful. This just does the same thing as capacitors do. And it makes sense. If you look at the electromechanical analogy, a car that is whose engine is switched off eventually comes to a stop by air drag, and that expression is given by that. Let's go on to the charging circuit next. Charging circuit is slightly more complicated because you have a battery attached, so I will not pursue the analogy of energy anymore. Instead, let's just go back to KVL. So I'll take this loop and let that be the direction of travel. Now remember, when this battery first starts putting current through the inductor doesn't like it one bit, and according to Henry's law, there's going to be a mighty back EMF opposing that change. So that's the situation there. Let's write KVL for this. Starting from the battery, I'll get positive E, and current is flowing in the same direction as the loop travels, so that's going to be negative IR. And here I'm going to get an anti-battery because of that back EMF. So I have to use a negative sign in Henry's law. L di by dt equals 0. Well, the one thing I can do here is to move di by dt to the left, and then I'll have to divide both sides by L to do that. So I'll get E over L minus I R over L times I. Now L over R is tau, so R over L is 1 over tau. So we're back to the same thing. Di by dt equals E over L minus I over tau. When you try to separate the variables, you're not going to have an easy time like this one. So you're going to have to separate the whole thing. So let me do this off to the side. So as to save some writing. I don't really think it will save some writing. But let's use the electromechanical analogy and think of this as velocity, dv by dt. And let me call this A and A plus bx, bv. All right. Let's try to solve this basic equation. So that gives me dv over A plus bv equals dt. Integrating both sides, I'll get natural log of A plus bv, but I have to divide by b. So 1 over b equals time t plus some constant. Now I'm going to write this constant in a very special way. I'm going to write this constant as 1 over b natural log of the constant. You'll soon see why. Multiply both sides by b, and I'll get natural log of A plus bv equals t plus just ln con. And now I'll take the exponential of both sides, so I'll get A plus bv equals con times there's a b here, e to the bt. So now I'll solve for v. First I'll do bv. bv equals negative a plus con e to the bt, and finally v equals 1 over b negative a plus con e to the bt. Done. So I've solved the equation. All I have to do now is make a one-to-one correspondence between what a and b are. I is of course velocity, so that's fine. A is this quantity E over L, and B is the quantity, so I'll write it here, B equals negative 1 over tau. So once you have made the one-to-one correspondence, I can just simply write my solution. My solution is the current as a function of time is equal to 1 over B, which is negative tau, times negative A, which is negative E over L, plus con e to the bt, which is e to the negative t over tau. Everything looks great except for this ugly looking con. So let's dispense with it by doing our initial conditions. And that's simple. At t equals 0, the inductor was empty. So I of 0 equals 0. Otherwise you would not be charging it. And that's not really true. You can put some other value if you like. I don't care, but this is the simplest. So put that initial condition. I'll get 0 equals negative tau, by the way, is L over R. So let's just use that. If I do L over R times E over L, I'm going to get E over R here. So E over R minus tau, which is L over R, times con e to the 0, because t equals 0. This clearly tells us that con times L has the same units as E. So I'll get con equals E over L. So I've determined the constant of integration, it's E over L. Now I'll substitute it back there, and I'll get my full-fledged expression. Whoa, excuse me, had some mishap over there. So I'll get I of t equals negative tau, which is, well, I just did all that. So it's E over R minus L over R con. Well, if I do, the con is E over L, so I'll just get E over R again. E to the minus t over tau. And I can simply take E over R outside. So I'll get 1 minus E to the minus t over tau. So this looks rather like the formula for charging up a capacitor, does it not? Where you have Q instead of I. So this quantity, E over R, for that reason, is called I infinity. In the same sense as we had Q infinity while charging the capacitor, you have I infinity. It's the asymptotic value of the current when all the charging is done with. So this is these are the equations. And once you have the current, you can of course find the corresponding voltages by simply using the different laws, be it Henry's law or Ohm's law. Now in the subsequent videos, we'll be doing the other kinds of circuits and their appropriate mechanical analogies, but this is like the first circuit with a mechanical analogy. Remember, we cannot have any mechanical analogy for the RC circuit. That was the first circuit we did, but that did not have a sensible mechanical analogy because capacitance is like a spring. So you have a spring with air blowing on it. Doesn't really make much of a visual sense.